We know how to find the electric field intensity if we have a point charge or a series of point charges. We can utilize that to find the electric field intensity if we have some sort of charge distribution, such as a volume charge density or a line charge density or a surface charge density. Let's look at the situation where we have some volume charge density and we want to find the electric field intensity at some point that has position vector r. Let's first recall how to find the electric field intensity at some point due to a point charge. We have a point charge q at position vector r sub q. We want to find the electric field intensity at a point whose position vector is r. First recall the force on q sub t found from Coulomb's law. Now if we take and divide both sides of this equation by q sub t, we obtain our electric field intensity at position vector r. If we look at a differential volume inside our charge distribution, there is some charge associated with that differential volume. That charge will be the volume charge density times our differential volume. So we can treat this as a point charge and write the corresponding electric field intensity at position vector r due to this point charge. R is the vector that points from the point charge to where we want to find our electric field intensity. I'll call the electric field intensity due to this differential charge at location r dE, and it's equal to 1 over 4 pi epsilon sub 0 times the differential charge, which is rho sub v dv, over the distance squared, r squared, and it's in the direction of this vector r, and here's the unit vector pointing in the direction of the vector r. Since superposition holds, we can sum up the contributions to our electric field intensity due to all the differential point charges over our volume. So we do that by just integrating over the volume of our charge density. So here's how you'd find the electric field intensity if you had some volume charge density. The concept is simple, but the implementation, even for simple charge distribution, is difficult. Let's look at finding the electric field intensity due to an infinite line of charge of line charge density rho sub L. An infinite line of charge on the z-axis will have a cylindrical symmetry. We'll work in the cylindrical coordinate system, and in that system the electric field intensity will depend on rho, phi, and z. And in general, the field can have a component in the rho, the phi, and the z directions. We'll see that the cylindrical symmetry means you won't have all these components, and the components you have will not depend on all the variables. Imagine a positive test charge at point P, and let's assume the line charge density is positive. The test charge will be pushed away from the line, so there will be a rho component. If you think of a differential charge, a distance z prime above P and minus z prime below it, you'll see that the forces in the z direction cancel out, and you can account for all the charge along the line by these pairs like this, so you can argue there will not be a z component of the electric field intensity. At point P, the phi component is into the page, and clearly the charge along the z-axis is not going to push the charge in the phi direction. Consider this view of looking down the positive z-axis. So this red dot here represents the line of charge coming out of the page. And this is just an imaginary circle drawn around the z-axis. So at any point along that line, if you put a positive test charge, it would be pushed in the rho direction. There would be no force in the phi direction being a tangent to this line. So there's no electric field intensity in the phi direction. The electric field intensity will depend on rho because as rho increases, you're getting further away from your line charge. The electric field intensity will not depend on z because no matter what z location you go, your view of the infinite line charge is the same. You still have an infinite amount of charge above you as you do below you. So there's no z dependence. Going back to this view, looking down the positive z-axis, at a fixed distance from the line of charge, the magnitude of the electric field intensity is always the same, and it's always going to be in the rho direction. So the electric field intensity also does not depend on phi. From the cylindrical symmetry, we see that our electric field intensity will only have a component in the rho direction and only depend on rho the distance you are from the line of charge along the z-axis. Our line charge is only along the z-axis, so dl is going to be dz. So each dl will have a charge associated with it, and so that differential charge we'll call dq, and it will equal rho sub l dz. Let's pick the point P here on the xy plane, a distance rho from the line charge, to find our electric field intensity. Since the electric field intensity only depends on rho, then it doesn't matter that we picked a point on the xy plane, because if we move in the z direction, we'll get the same result as we did on the xy plane. R is the vector that points from dq to the point P where we're going to find the electric field intensity. It is the sum of this vector plus this vector. This vector has magnitude z and it's in the minus z direction. This vector has magnitude rho and it's in the rho direction. The magnitude of r is the square root of z squared plus rho squared. A unit vector in the direction of our vector r is just the vector r over the magnitude of r. So the contribution to the electric field intensity at point P we'll call dE due to this dQ, and it's equal to 1 over 4 pi epsilon sub 0 times our dq, which is rho sub l dz, over this distance squared, and it's in the a sub r direction. To get the total electric field intensity at point P, you just have to sum up the contributions from each dq from minus infinity to plus infinity. The rest of finding the electric field intensity has nothing to do with electromagnetics, but has to do with performing this integration. Let me just outline a method for finding the final electric field intensity. The magnitude of dE is just our differential charge, rho sub l dz, over 4 pi epsilon sub 0 times this distance squared, r squared. We know the components in the z direction will cancel when we integrate from minus infinity to infinity, so we need to just sum up the rho components as we integrate from minus infinity to infinity. If we call this angle alpha, then this angle in here is also alpha. So the rho component, d sub rho, is dE times the sine of alpha. So we'll substitute this in for dE. So we have an expression for the rho component due to this dQ up here. To get the total electric field intensity, then, we will sum up the contributions from z equals minus infinity to plus infinity. To finish off this integration, we need to do some change of variables. And I won't go through and bore you with those details. They're in the notes I handed out. But here is our end result for the electric field intensity due to an infinite line of charge on the z-axis. It is the line charge density over 2 pi epsilon sub 0 rho, and it's in the rho direction. Recall that when we had a point charge q at the origin, the electric field intensity fell off as 1 over r squared. Now that we have an infinite line of charge on the z-axis, the electric field intensity falls off as 1 over rho, 1 over the distance from the charge.